Hey guys, today we're going to do a video on symbolic problems, or where did all the numbers go? Alright, now, what is a symbolic problem to begin with? Well, a symbolic problem is a question where they don't give you any numbers. Instead of saying something like, a ball is thrown vertically upward at 9 meters per second, determine the maximum height and the time of flight, and whatever else they might ask, instead of giving you a number for that initial velocity, they might say a ball is thrown vertically upwards with an initial speed of v naught. And you're supposed to find the maximum height for that ball. Well, so probably most people's first reaction is, what? Like, how can I find the height that it goes to without actually knowing the initial velocity? However, I'm going to make a prediction, and that is this. As you go through the school year in physics, you're going to discover that you actually like symbolic problems more and more. Most people at first have a really hard time with these because they're symbolic, they're abstract, right? You don't get a particular answer, like 18 meters or something like that. You get answers that look like this. And a lot of people find that at first to be really upsetting and disorienting. Like they don't even really know how to make sense of that. But as you get further in, you will grow to prefer symbolic answers. Number one, because you won't have to get out your calculator. At least that's how I feel about it. You just do algebra and then you have the answer. But more importantly, they give you a universal answer that you could plug any set of values into that you wanted to. And they also show you the relationship between the variables in question. So if this is the expression I have for like the height that a ball goes to, I could plug in the initial velocity, whatever that happens to be, to find the height that it would go to on any planet. Right? I could have different values for g. So this works for Earth, Mars, the Moon, whatever. And also it shows me that since the initial velocity term here is squared, the maximum height depends on the square of the initial velocity. Meaning that if you double that velocity, it would in fact, 2 squared is 4, quadruple the maximum height that the object would go to. So the point of a symbolic problem is to demonstrate the relationship between the variables and give you a general solution rather than a particular solution, such as 5 meters. They can't really be applied to any other situation. Okay, so that's what they are and why we do them. Let's do a particular example. So here we have a ball that is going to be dropped off the back edge of a triangle for some reason. All right, and then another one that's going to be rolled down it. All right, and we're told that the height of the incline is h and the length of the incline is 2h. Okay, all right, now part A wants us to calculate the final velocity of the ball that is dropped, and it says in terms of h and g. All right, now it's very important for symbolic problems that you know what you're allowed to answer in terms of. Meaning this, if I am told the height of the incline is h, I can't answer in terms of things other than h, or fundamental constants. So g can always be in your answer. The number 2 could always be in your answer, all right, or square root of 3 or pi or other things like that. But I could not, for example, answer the question in terms of time, all right? So if I tried to do something like this, I said, well, v equals v naught plus at, all right? This is wrong. This is the wrong way. Let me just go ahead and say that this is wrong and do it the wrong way so you can see what not to do, all right? Well, final velocity is what I want to know. I could say the initial velocity is 0. The acceleration is going to be negative, you might be thinking 9.8, but when we're doing symbolic problems, we don't say negative 9.8, we say negative g. And then, let's see, t. I guess I'll just say that it's t, because it's a symbolic problem, and I don't know what else to do. There, my answer, negative GT. Got it. No, absolutely not. The reason you can't do this is nowhere in the prompt does it say the ball is falling for a time t. What it does tell you is that the height of the triangle is h. And so you have to answer in terms of h, and you may not answer in terms of t. All right, now you might later on in the problem solve for the time that it takes to fall, but that answer will be in terms of h, right? Not in terms of anything else. So h has to be in the solution because they gave us h to begin with. All right, now, if they had said the ball falls for a time t, then t is allowed to be in your answer. So just look at what the givens are. Also, most of the time they will kindly say in terms of whatever. So if they say in terms of h and g, that's what's allowed to be the answer. And also remember other numbers and constants like the square root of 5. That's always allowed to be in there. All right, well, looking at the problem, I'm going to presume that the ball is dropped. Both of them, we're going to say, are released from rest. So I can say the initial velocity is 0. Okay. Also in symbolic problems, you can make other assumptions that we generally make. Like if something is thrown straight up, the vertical velocity at the top is going to be 0, because that's how it is for everything. Even if it's a symbolic problem, 0 is still a valid input. All right? Okay, so the initial velocity is 0, because it's released from rest at the top of the triangle. The acceleration for the one that is dropped, right? This is for the one that's dropped. That's going to be negative g. And the other thing that we know is that it falls a height of h. So that means I'm going to put for delta y, careful now, negative h. Why negative h? Well, because it goes down. If it went up a height h, because it were tossed upwards, well, then we would have h. But this is falling downwards, so negative h. And then the thing that we're looking for is the final velocity. That would be the letter v. So based on what we have here, I am going to use the time-independent equation. Okay, and I'm just using delta y here because this is a vertically oriented problem, right? Your generic equation says delta x in it, but it could be delta y or delta z, whatever. Depends on what day of the week it is or something. All right, now, v is what we want to know. We said v naught is 0 because it's dropped. And we have 2 times negative g and negative h. So 2 negatives make a positive. Oops, don't forget to carry down the square. Whew, that was a close one. And I'm going to have v squared equals 2gh, which means that v is the square root of 2gh. All right, I would actually remember that solution because that's going to come up all the time, like all the time. Anytime something is dropped from a height of h, that's actually going to be its speed when it hits the bottom. If it's thrown downwards, then it's a different story. But if you just drop it, it's root 2gh like every time. All right, so that's part A. Wonderful. All right, now, B wants to know, well, let's see. If we read it through, it says, the final velocity of the ball that rolls is 1 over the square root of 3 of the answer above. Determine its acceleration. Well, that sounds like a doozy right there. So let's again write down what we know, starting with the final velocity, because that's maybe the trickiest part. So the one that rolls down the incline, it says its final velocity is 1 over root 3 of the answer that we got above. So hopefully we got an answer above. And oh, there it was, root 2gh. So it's root 2gh over root 3. Okay, so that's the final velocity for the ball that rolls down the incline. All right, let's write down the other things we know. If you feel like you know how to proceed from here, as usual, pause the video, get a little bit ahead of me, and then check and see if you did it right by resuming the video, but let's see. All right, the initial velocity is 0 because it's released from rest at the top, or at least that's sort of, I hope, implied by the picture. All right, the displacement. All right, now I could say negative 2h or 2h here. They don't really tell me anything about the sign that I'm supposed to be using. Also, while we're thinking about signs, let me cut back to over here real quick. Probably it would be better if I said for this answer here, negative root 2gh, because of course it's going down when it hits the ground. Fine, so really this solution is just the speed. I'm going to go ahead though and for part B say that down the incline is the positive direction. For really just because I can, and because then I don't have to get too fussy with signs, all right? So this is going to be the positive direction. All right, so that means I'm going to say that well, let's just call it delta x is, let's see, 2h. All right, and then we're supposed to find the acceleration. All right, well, once again, that's directing me towards the time-independent equation. And if I plug in all the stuff, I should have, let's see, root 2gh over root 3. That's getting squared, though. 0 for the initial velocity. Don't know the acceleration. And 2h for the displacement. All right. Now, squaring that, I'm kind of running out of room here. Maybe I'll erase my wrong work up there. Squaring that, I'm going to get 2gh over 3 equals, well, that's going to turn into 4ah. All right, now if you forgot what we were solving for here, it's the acceleration. So let's see, h cancels. We'll divide both sides by 4, and after a little bit of work, I'm going to get that its acceleration is g over 6. Let's put a box around that. That looks good to me. All right. Now, if they went on to another part and asked about the time, we might have to do a little bit extra here. So let's go ahead and make up a part C so that you can see how it might work if we have to do some other equation. Since I used the same equation both times, we probably need a part C. All right, so regarding the question of time, if both are released simultaneously, we want to know how much time passes between the moment when the dropped ball strikes the ground and when the rolled ball finally arrives at the bottom, right? Clearly this one's going to take longer to get to the bottom because, of course, it's rolled down the incline rather than dropped straight there. Okay, now, if you think you know how to do it, again, pause the video. You're going to use the information from the previous parts of the problem, but maybe not all of the parts, okay? So figure out what's most useful. There is more than one right way to come up with the time interval, although some ways are easier than others and involve less algebra. So pause me, get a little bit ahead of me, and then resume and see if you have it figured out. Now, I have chosen to use what I am calling equation number 2. You could also have used equation number 1, which is v equals v naught plus at, but I prefer to use this one because I think the algebra looks less disgusting, because I'll have to use things with radicals in it for this. Okay, now, initial velocity is 0 for both of them. Next, I got to plug in the accelerations. All right, I'm regretting some of the decisions I've made about signs and letters and stuff because it's potentially confusing, but this would be the next line down. Now we need to solve for the time. Seems that the dropped ball takes the square root of 2h over g seconds to land. All right, and there's the other time. All right, now I'm not sure that subtracting the answer is going to be particularly interesting, but you might notice, look, they look very similar, but the other one is the square root of 12 times larger. That's how symbolic problems work. All right, hope this was helpful.